For the past 2 lessons, we focused on graphing exponential functions. Today we're going to switch gears a little bit and we're going to talk about applications. All right, so one place that exponential functions are very commonly used is for calculating compound interest. What compound interest is the following. Suppose you go and you put money in a bank, right? What happens? The first month the bank pays you interest. So, you know, like if you had $1,000 in there, now you have like $1,001, right? $1,001. And then the following month when they're going to give you interest again, they give it to you on the new sum, right? On like the 1,001, not the original. That's compound interest. The formula for compound interest is this, and I know you've seen it before. It's P1 plus R over N to the power of NT. Let's talk about what each of these things mean. The A here, first of all, is the final balance in the account. So when you get your statement, how much money is in the account now? For the time being, if you have your calculators out, just put them on your desk face down if you want to resist the urge of playing with them. P is the principal, right? And that's not Miss Howard. That's how much money you go to the bank to deposit to open up your bank account. So P is the initial amount that you put into the account. All right. R is the rate in decimal form. So basically, if the rate is 5%, you have to divide by 100 in order to get the decimal equivalent. Okay? T is time in years. Okay, so here's what counts. It's N. N is the biggest thing you need to worry about right now. That number N, it shows up in the denominator and in the exponent there. N is the number of times within the year that the bank pays you interest. And this depends on the type of bank account you have. So, if you're told that interest is paid or compounded annually, how many times does annually happen within the year? Once. So, if it says annually, N is 1. Semi-annually, how much is N? 2. Quarterly, N is 4 because 4 quarters in the year. Monthly, 12. Daily, 365. Okay, so the one thing that's not on here is weekly, and I get you asked every single year. What's weekly? How many weeks are in the year?
52.
52. You're going to remember that, okay? 52 weeks in the year. Okay, so here we go. Mrs. Algebra invested $2,000 into an educational account for her son, right? Her maiden name was Miss Trig, and so now she's Miss Trig Algebra. Okay, so when he was an infant, the account has a 5% interest rate, right? She invested $2,000. If Mrs. Algebra does not make any other deposits or withdrawals, what will the account balance be 18 years after if the interest is compounded as follows, right? So 18 years after, like when the child is now ready to go to college. There you go. So, what are we given here? What's the 2,000? So, we have here A is equal to P, 1 plus R over N to the power of NT. What's 2,000? It's the initial, so what letter? That's P. Okay, what about the 5%? What's that? That's your R, but how do you use it? Not 0.5, 0.05. Okay? 18 years is your T. So I actually want to write it down here. So P is 2,000. R is 0.05. T is 18. Now for this one, it says it's being compounded quarterly. So what's N? N is 4. We're going to plug it into the formula. P, 1 plus R over N to the power of nt. So that's 2,000. 1 plus 0.05 over 4 to the power of 4 times 18. Okay. So we have 2,000 times 1. You have to put it in as you read it, right? 1 plus 0.05 over 4. Close the parentheses, to the power of 4 times 18. Okay, so look at that. Right? When you are done, it should look like what you have on your paper. So that's $4,891.84. So A is 4891.84. Okay, before you move on to the other one, please stop for a minute. Regardless of how many decimals the calculator gives you, you know that this is dollars and cents, and you know that you have to go to 2 decimal places. I'm not going to, listen, I'm not going to tell you in the problem how many decimal places to round to. And even if you ask me, I'm not going to tell you. Furthermore, you have to round properly. So if this had a, 0.845, you have to round properly, right? Otherwise it will be points off. Okay? All right, now, for the next one, it's monthly. So what's going to change is N is going to be 12. So A is 2,000. 1 plus 0.05 over 12 to the power of 12 times 18. Okay, so here's what, please everybody look up here for a minute. Don't plug anything and look up here for a minute. Here's what I need you to do in this case. Press the up arrow once, twice. That highlights this for you. Press enter, and now you get it in editable form. Press the left arrow button and go and edit in order to minimize error. You can even hover, bring the cursor to where you want it to go, click, edit, right? You have paid lots of money for this calculator, and you want to be able to use its functions. We could have done it with the TI-84s as well. So now, A is $4,910.02. So from going from quarterly to monthly, right, we were getting 892-ish. Now we're getting more money. Okay, so next it's daily. A is, what's N now? 365. So 2,000 over 365. Right? Again, I go up, up, enter. And I'm going to edit. Okay, so look at this one. What do I write? 4918 point what? It's 9, so I do 90. Okay. Okay, so take a look at what happened here. In one case, we were getting paid quarterly, 4 times a year. We're making $4,891, right? At the end of 18 years, that's how much money I was going to have. Then I found another account which gives me interest every single day. So you think, oh my God, like you're going to be a millionaire in 18 years. But no, how much of a difference is there? It's over 18 years, right? It's like 19 plus 8, like $27 over 18 years. So that's the difference. So in going from quarterly to daily, the amount that increases is $27 for 18 years, right? So it's not that big of a difference. Yeah. This is homework. I need to see 3 things. 1, you've written down the given. 2, you've written down the equation. 3, you've substituted properly. Okay, so that's 3. I need to see these 3 things. So, if it's an ABC, right, you can write number 1 one time. You can write number 2 one time. But this, individually, it has to show up every single time, and then obviously the final answer. That's if you want credit. Now, if you're just doing it for the fun of it and you don't care if you get credit, then that's up to you as well. Okay? All right. Now, so take a look. Mrs. Algebra does the math, because she's Mrs. Algebra, and she figures out, you know what, with any of these accounts, okay, so even if I go to daily, right, I'm only increasing my profit by $27 over 18 years. And she's like, you know what, I don't like any of these accounts because I want to be rich by the 18 years. I want my son to have, like, not to worry about anything. So then she goes and she hears about this thing where the bank pays you interest continuously. And from that we get the continuous compound interest formula. So here, it's not that the bank is paying you one time a year. It's not that they're paying you every single day. No, it's more than that. The computer is calculating interest and paying you every nanosecond of every second of every day. So it's like, you just got paid again, got paid again, got paid again, got paid again, got paid again. So imagine how much more money that account is going to pay. So now, when that happens, when it goes from, monthly, daily, to continuously, now the formula shifts a little bit, and now the new formula is everybody's favorite, A equals PE to the RT. You only use this when you hear the word what? Continuous. Okay? Continuous. A equals PE to the RT. So, Mrs. Algebra found an account that will pay 5% interest compounded continuously on her $2,000 investment. So here, P is 2,000, T is 18, R is still 0.05, and now A equals PE to RT, 2,000 e to the 0.0518. Let's plug that in. 2,000 e to the power of 0.05 times 18. Oh my God, a whopping 4,919 and 21 cents. So over the 18 years, how much more money than the daily? Not even $1, because this is 8.90, so it's like 31 cents over the 18 years. Why does that happen? Because it's E, because it's that equation that I said yesterday. Yes, it starts to increase and then it plateaus. Okay? Anyway, you don't have to know that much background, but that's pretty much how it works. All right? So we use that only when we hear the word or see the word continuously. Okay, so money is not the only place we use math. The same principles apply when we're talking about population growth, bacteria, when you're talking about radioactive decay. carbon dating, right? When they find fossils, how do they know how old the fossils are? Because every living thing has carbon in there, and carbon decays at a specific rate. It has what we call a half-life, and so based on how much carbon there is in the sample, they can figure out how old it was. Okay? So, the formulas here, these formulas are the original formulas from where the compound interest formulas came. All right? So, in addition to investments, here is where they are used. Your book uses these versions of the formulas with the n's. N equals N naught, blah, blah, blah. So let's talk about what this is. N is the final amount. N naught is the initial amount. Okay? It's N subscript 0, we call it N naught. R is the rate, T is the time. Okay. Every other book in the universe uses Y instead of N. And that's actually like the original preferred one. So Y equals Y naught, 1 plus R to the T. Okay? Now, if what you're talking about is increasing annually, monthly, whatever, like for example, rent prices, right? If it increases by like 5% a year, you use this one. If population is increasing by 10% annually, you use this one, okay? Now, if the amount is increasing, you use positive R, so 1 plus R. If the quantity is decreasing, use negative R. So it'll be Y equals Y naught, 1 minus R to the power of T. And again, this is for problems where they increase once a year, rent, salary, and so on and so forth. Or if it decreases, right? So if the value of a car depreciates or decreases by 3% every year, that's the one you're using. Okay. The other one is the continuous growth or decay. This is N equals N naught e to the kt. It looks like A equals P e to the RT. Alright? Or it's Y equals Y naught e to the kt. Again, this is initial. This is final. Okay, take a look. Everywhere else, the rate is given the symbol R. Only in the continuous case is the rate given the symbol K. We're not going to take it upon us to change that. We're going to use it as it is, but that's what it is. Okay? So, this looks like A equals P e to the RT, right? So, somebody's going to ask me now, can't we just use A per for the population? And you know what the problem is there is? The answer there is no. These are the OG formulas. These are where everything came from. The bankers, because they couldn't deal with Y's and Y naughts, they needed to put in there monetary, like banking vocabulary. So they said P for principal, you know, and all that good stuff. So these are the ones. You're not going to use A per for population. That's not cool. Okay? All right. And again, if the quantity is increasing, positive K. If the quantity is decreasing, negative K. And you have to use the word continuously. You have to see the word continuously. Okay.
We don't have to use it. If this is like that order,
What do you mean?
Like, it says continuously. This or.
Okay, so what I was just saying is APERT is only bank accounts. If you have anything else, car losing value, house increasing in value, population, bacteria, rabbits, foxes, whatever, N equals N naught or Y equals Y naught. Okay? So here are the terminology. So N and N naught, final and initial, and remember that it's R or K for rate. Okay. A state's population is declining at a rate of 2.6% annually. Okay. The state currently has a population of approximately 11 million people. If the population continues to decline at this rate, predict the population of the state in 15 years or 30 years. So let's first write down the given. First of all, which formula am I going to use for this? The first or the second? The first. So it's going to be N equals N naught. Y or N? Either one. N equals N naught. And because this is declining, it's going to be minus, right? So here I'm going to do 1 minus R to the T. Yes. Not the not symbol, it just stands for initial. So instead of using different letters for initial and final, like F and I or A and P, you can just get away with one letter, right? And then N is the final amount, and naught is the initial amount. Okay? Yeah, it's just that like that little symbol, it's the initial amount. That's what it means.
I thought the one that equals the final. Oh, because it's N naught.
It's basically just like a symbol.
Yeah, it's like a little accent mark. It's a symbol. Okay, so rate, right, is 0.026. The state currently has a population of 11 million people. That's the initial. So that's your N naught. And we're not going to say 11, okay, let's just write down 11 million. What are we looking for? We're looking for N, the final amount. And here, we're given that T equals 15. So N is equal to N naught. Now, in our formula, we're not going to put the million. We're just going to put 11, and we're going to know that it's talking about millions. 1 minus 0.026 to the power of 15. Because it says in 15 years. So now when I go to the calculator, it's 11, 1 minus 0.026 to the power of 15. And that's 7.4093. So, what does this mean? In 15 years, there are 7.4 people left? Million. So, this is approximately 7.4 million people. All right? You can. However, then you're sitting there counting like 6 zeros, and then what if you mess up and like, you know what I mean? There's just so much room for error. You could, and then like transferring the answer back here, I just see so much room for error, right? Mathematically, there's nothing wrong with it. So this is 11 again. Now for 30 years. The rate is negative. 1 minus 0.02. So again here, we're going to modify, edit. We're going to go to 30 years. Now there is 4.9907. So that's approximately 5 million people. It's not looking good for these people. Table that shows the number of reported cases of chickenpox in the United States from 1980 to 2005, and this is a real data set. Okay, so look here, in 1980, there were 190.9 thousand, okay, and then in 2005, there were 32,000, so it dropped significantly, right, from 190,000 to 32,000. If the number of reported cases of chickenpox is decreasing at an exponential rate, identify the rate of decline. So that means we want to find what R is and write an exponential equation to model the situation. Okay? All right. What we're going to use is n equals n naught, 1 minus r to the power of 2. Right? So, n is the final amount. In this case, look at what we have. N naught, the initial amount, is 190.9. The final amount is 32.2. And how much is t? How much time has passed? 25 years. Let's plug that in there. So n, 32.2, equals 190.9. 1 minus r to the power of 25. Oh my, what we do now. Okay, let's divide by 190.9. So I have 32.2 over 190.9 is 0.168675. I want to use as many decimal places as I can in the intermediate steps. Equal to 1 minus r to the power of 25. Okay, now how do I get rid of an exponent? Root 25. So root 25. Okay? Why? Because if I have like x squared or x cubed equals 7, what do? Cube root, right? Same thing. So now look at how I'm going to do this though. On this right side, I'm just going to end with 1 minus r. Here, it's going to be, where is it? Control this one, right? And so look, in the index, I'm going to put 25. In this, instead of plugging in the values again, I just put in control, answer. Okay? Enter. Answer. It's the negative button. So I get 0.9313. Now what am I going to do? Minus 1, minus 1. So minus 1. Negative 0.0687 equals negative r. Right? And so what's r? Negative 0.0687. Oh, sorry. Huh? Yeah. But now it says, write an exponential equation to model the situation. So what's the exponential equation? It's n equals n naught one minus r to the power of t. That's the equation. For the equation, you have to substitute everything except n and t. Okay? Because if it's an equation, you need two variables. Okay, now it says graph the equation and use your model to predict when they will drop below 20,000. So let's graph it. What's the equation that we came up with? So n equals 190.9, 1 minus 0.0687 to the power of x. Okay? Okay. So now when you graph, you're not going to see much. Why not? Because look at my values. First of all, what does the x-axis represent here? What does the x-axis represent? This represents years, right? So t in years. And what is the time frame for my problem here? It's going from it's like 25 or so years, right? So why don't we go to the window and change that? And how about the y-axis? The y-axis is the number of cases. And that, it was like 190 at the beginning, right? So let's go to menu, window, settings. The x-axis, we're going to go from 0 to, let's go to 50 years. The y-axis, we're going to go from 0 to, what was that highest number? It was like 190, so we're going to go to 200. Well, this is why we're running it. Huh? Yeah, you try to copy it, but also it says to predict when the cases will drop below 20,000. So it looks like this. And so when you trace here, menu, before, because you were only seeing from like negative 10 to 10. You were only seeing this part of the window. Because that's how your setting is on the calculator. It only shows from negative 10 to 10. You have to expand it. So, look, when you trace here, this is the number of years. This is the number of cases. You want to see where it dropped below 20,000. These are in 20s. These are in thousands. So this one here is 32,000. So you want to traverse the curve. You want to move to the left and see when it was 20,000. Oh no, you want to go to the right, sorry. When does it hit 20,000? 25, 24, 23, 22, right? So somewhere about here, so about 31 years.
Should we just write about 31 years?
Just a sec. Okay, so all right, so when the cases will drop, about 31 years, when did we start? When did we start? In 1980. So or in 2031. Okay? All right, and that's the homework for tomorrow.